not exist non-zero integers a and b such that a squared equals p times b squared. This is equivalent to showing that the square root of p is irrational. We'll use proof by contradiction. First, let's assume the opposite of what we want to prove, that the square root of p is rational. This means it can be written as a fraction ab, where a and b are coprime integers. Squaring both sides, we get p equals a squared over b squared, which gives us a squared equals p times b squared. Looking at our key equation, p times b squared equals a squared, we can see that p divides a squared. Since p is prime, by Euclid's lemma, if a prime divides a product, it must divide at least one of the factors. So p must divide a, which means a equals p times some integer k. Now we substitute a equals p times k back into our original equation. This gives us p times b squared equals p squared times k squared. Dividing both sides by p, we get b squared equals p times k squared. This means p divides b squared, and since p is prime, p must also divide b. Now we have a contradiction. We've shown that p divides both a and b, but this contradicts our initial assumption that a and b are coprime, meaning they share no common factors other than 1. These two statements cannot both be true simultaneously. Since our assumption led to a contradiction, it must be false. Therefore, we've proven that there do not exist non-zero integers a and b such that a squared equals p times b squared. In other words, the square root of any prime number is irrational. This means numbers like the square root of 2, 3, 5, and all other prime numbers are irrational. The discovery of irrational numbers had profound historical significance. The Pythagoreans were reportedly shocked when they discovered that the square root of 2 could not be expressed as a fraction, contradicting their belief that all numbers could be represented as ratios. This elegant proof demonstrates the power of mathematical reasoning to establish fundamental truths about